Hi everyone, and welcome back to Nuddle, the go-to place to learn about finance, econometrics, data analytics, and much, much more. My name is Sava, and truth be told, I missed the channel and I missed you loads. So, coming back, I thought it's quite fitting to revisit the very first video I have ever recorded for this channel back in 2019, and some of the old subscribers will remember it was about value at risk modeling, the basic market risk measurement technique, and I thought it's high time to revisit the value at risk, talk about the most efficient, user-friendly way of modeling it in Excel, and discuss three most common techniques of estimating basic value at risk, which are the parametric normal, variance covariance VaR, the historical simulation VaR, as well as the Monte Carlo simulation VaR. And again, we'll also discuss return versus money form, reporting of VaR, and scaling of value at risk across frequencies. So we'll investigate daily VaR and weekly VaR and learn how to best represent those. And alongside the calculations, we'll also discuss assumptions, applicability, and limitations of the three techniques. The data we have got today is quite standard. It's 5 years worth of daily data on the S&P 500 Tracker Fund, SPY. Calculating daily returns is simple. The value of the index today divided by the value of the index yesterday minus 1, and that can be calculated throughout the sample. We have got 5 years worth of data translating into 1255 daily observations, guided by Basel III. It's quite typical that banks will use 5 years worth of daily data to backtest their VaR and to perform their calculations. For weekly VaR, we need to mind that we have got 5 trading days in a week typically. So for historical simulation applications in particular, we need 5-day holding period returns. And it's easy to do because here we have got 5 first days, then we have days 2 through 6, and so on. So the way of calculating holding period returns, keeping in mind the continuous compound nature of returns, is to use product 1 plus, refer to the 5 daily returns, and subtract 1. That would give us the understanding that over the first 5 days, the holding period return has been 7.38%, and again, an extension of it would apply it to the entire sample. It will have 1251 overlapping 5-day holding periods. For our parametric normal, variance covariance VaR, we simply need the parameters, and it's 2 parametric. It just needs mean and volatility, or scale. And so for the mean, we can use simple average of daily returns. And for volatility or scale, we can use sample standard deviation, stdv.s, of daily returns. And for weekly scaling, we can simply scale the parameters themselves, keeping in mind that the mean scales linearly. So a 5-day mean is just 5 times the daily mean. And volatility scales as a square root. Again, that assumes return independence, but long story short, if variance, so square of volatility, scales linearly, so 5-day variance is 5 times daily variance, 5-day volatility is daily volatility times the square root of 5, or however many periods we're extending it to. Just some assumptions before we move forward. Let's say our portfolio value is $1 million. Again, this can be scaled to any monetary value. This is for us to be able to report money VaR later on. And we have everything that we need for our first VaR technique, parametric normal variance covariance VaR. We need to input confidence intervals, and those 5 are perhaps the most widely used. Again, 97.5, 99, and 99.9 are the ones that are more conservative. Again, they talk about losses in most extreme scenarios. 90%, 95% are less conservative, and they have been used more historically. But nothing prohibits us from estimating value at risk for all 5. So for daily output, we need the inverse normal distribution function. Again, that is because this parametric VaR assumes normality. Nothing prohibits you from estimating parametric VaR for any other distributional assumptions. Here we input the probability, or 1 minus the confidence interval. We lock the column on the confidence interval because we want to drag it across for 5-day VaR. And then we plug in our parameters, mean and volatility, with rows locked. This allows us to estimate daily, so 1 day ahead, parametric normal VaRs, and we see that the more stringent the confidence interval, the greater in magnitude is the loss. Again, interpretation is quite simple. If we're looking at 90% confidence interval, it means that in 90% of cases, so 9 out of 10 days, our losses would not exceed 1.33% of portfolio value. 95% is, well, 5% of worst case scenarios, so 1 in 20 days, our losses would not exceed 1.72%. Again, only in 1 out of 20 days, our losses would be greater than 1.72% of our portfolio value. 97.5% means that in 39 out of 40 days, our losses would not exceed 2.06%. Here it's 1 out of 100, and here it's 1 out of 1,000. So again, in this percentage of cases, losses would not exceed that much. That's the interpretation of VaR. That's the cutoff value. Again, VaR is not concerned with what happens beyond the cutoff value at the extreme tail case, but it serves as essentially a threshold value beyond which losses will not go with certain confidence. And for 5-day VaRs, we can simply drag our formulas to the right, and that would use 5 days parameters, and because we have appropriately scaled those, these give us weekly, so 1 week ahead, or 5 trading days ahead, value at risk calculations. For historical simulations, it is both simpler and more complicated at the same time. We don't need to make any distributional assumptions, and we don't need to calculate any parameters. We need to use the empirical distribution of returns. That means just the returns that we observed here. And as we're using the historical distribution, we can use percentiles to estimate the likely losses. So it means that for daily 1 day ahead VaRs, we can use a percentile.exe, so exclusive percentile function, refer to the range of daily returns, lock in the rows, and as our threshold, we refer to 1 minus the confidence interval. And as we have got 5-day holding period returns in the nearby column, dragging to the right works just fine. Again, those missing cells are ignored by the percentile function, so the output is correct. And dragging down allows us to calculate historical value at risk figures for all the relevant confidence intervals. Here we can spot something quite interesting, that is, historical value at risk figures are roughly in line with the parametric normal VaR figures for lower confidence intervals, so for less severe cases. You get 90%, 95%, 97.5%, but they diverge for 99% and exceptionally so for 99.9%. And 1 in 1,000 loss, again, is not expected to exceed 7.17% in a week for parametric normal VaR, but for historical VaR, it is not expected to exceed 11.14%. So here the gap is quite noticeable. Similarly for 1 day ahead, parametric versus historical VaR, and the explanation for it is quite straightforward. The normal distribution underestimates the heaviness of tails of real-world asset return distributions, and that's why it might be a good idea to use heavier tail distributions or some other techniques to model real-world stock returns. while the historical VAR takes into account the real-world tail heaviness. However, it's not without its issues itself. First of all, both of those methods are essentially backward-looking because the parametric VAR uses historical data to calculate the parameters, whereas historical VAR essentially assumes that the return distribution is constant through time, and again, the extreme cases that we observed over the past 5 years are similar to the extreme cases we'll observe in the next 5 years, and that's an assumption that we cannot really avoid when trying to model the future with historical data. And the only method that we left to implement is the Monte Carlo simulation VAR. Again, here we are doing the basics. So the distribution we'll use for our Monte Carlo simulations is the normal distribution. And let's start with 1000 simulations. Again, to record those simulations, we can use the sequence function with 1000 rows, 1 column, and we'll just enumerate them, from 1 to 1000. For random numbers, we'll need random numbers from 0 to 1. Again, those will serve as inputs into our normal inverse distribution function. And for that, we can use the rand array function with, again, 1000 rows and 1 column. That produces random numbers from 0 to 1. Again, numbers that are close to 0 signify very bad days. So here, for example, day 4, we are closing in on the 5% threshold, so it's like 1 in 20 loss. Numbers that are close to 1 are good days, so here 0.9849, it's like 1 out of 50 extreme gain. And numbers that are close to 50%, say simulation 16, those are your average run-of-the-mill days, or the median days, essentially. And here we can use our estimated parameters to draw random numbers from the appropriate distributions. So for our one-day returns, we use normal inverse distribution, refer to the array of random numbers, we'll log the column here, and we refer to the one-day parameters, mean volatility, and we can do the same for 5-day returns with 5-day parameters here. And again, Monte Carlo simulation approach essentially combines some techniques from the parametric VAR and the historical simulation VAR. Here, we need to apply the percentile function to the simulations we have just performed. So for a one-day Monte Carlo simulation VAR, we use exclusive percentile function applied to the range of one-day returns, locking row, and referring to 1 minus the relevant confidence interval. And for 5-day VAR, we're doing the same, but with an array of 5-day returns. Dragging it down, enforces it through all of our confidence intervals. And now, having calculated the return form VAR, we can also calculate money VAR by essentially referring to minus our returns times the portfolio value. That would give us a representation of money loss that would not be exceeded in the relevant proportion of cases. Let's now compare all three methods. First of all, with 1000 simulations, Monte Carlo VAR is quite noisy. We see that if we perform any calculations, these numbers change quite substantially, and we see that they do fluctuate quite a lot. But if, say, we input 1 million simulations, then the output that we'll get is very close, in fact, almost identical to the output of parametric VAR. And that's unsurprising, as with infinite number of simulations, the output we get from a normal Monte Carlo simulation is exactly the result of parametric normal VAR. Again, For any other distribution, this would be also the case. Whereas for historical VaR, we are assuming no mathematical distribution function, and we're just looking at historical extreme events, especially here at the 99 and 99.9%. So what is the problem with, say, historical VaR? Well, first of all, it's also backward looking, but it's also problematic is that it assumes that all observations are equally important. So say extreme returns that occurred 5 years ago are as relevant as, say, extreme returns that occurred last month. And that might not be true for forward-looking modeling, especially like one day ahead modeling. What is also quite problematic across all three basic techniques is that they implicitly assume constant volatility, essentially that the volatility of stock returns is the same on each and every day, and that's quite famously not true of real-world financial markets. We observe volatility clustering, so periods of high volatility, periods of low volatility, and in particular we observe arch and gotch effects, so the tendency of volatility to be autocorrelated, so volatility to be higher after days of high volatility and low after days of low volatility. So for example, the very last day was a quite calm day with the return being 0.33%, so we might expect the next day, so essentially the start of November 2025, to be a comparatively calm day. Whereas if we look at volatility after a particularly extreme day, say 9th of April, here the return was very high, so again that's a very impactful stock market movement, and we have also quite impactful stock market movement on the next day, on the 10th of April. And these models do not account for that, at least in their basic forms. What is problematic for Monte Carlo simulation on its own are two limitations. First of all, computationally, it can be difficult, especially if you want to run millions or billions of simulations. And second, because it is, well, random, by definition, it can be manipulated, especially if the number of simulation is low. So if we go for, say, 1,000 simulations, what we can do is essentially report the outcomes that are most favorable to us. But again, because the Basel III mandates large simulation numbers, that's not necessarily a practical concern. And that's all there is for the application of three basic VaR techniques: parametric, VCV VaR, historical simulation VaR, and Monte Carlo VaR in Excel, with the discussion of return versus money VaR forms, some scaling applications, as well as their advantages and limitations. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any suggestions for further videos you might find interesting, and don't forget to subscribe to Nettle. Thank you very much, and stay tuned.